So in this section of the course, we're going to get ready to get into stresses, and we're going to talk about the conservation of mass and something called the divergence theorem. In addition to that, we're going to talk about the continuity equation and some other useful integral relations before we get into stress. So we're going to start off with something called the Eulerian continuity equation, which is basically an expression of the conservation of mass in terms of velocity, particularly for a fluid. If you were taking a class in fluid mechanics, you would likely go through this style of explanation of the Eulerian continuity equation. It's going to prepare us for a physical example of the divergence theorem, and we're going to take a fairly standard approach that's often used in fluid mechanics. So to do this, we're going to consider an unsteady or time-changing velocity field of a compressible fluid. So this fluid has a velocity field that depends on x, y, and z. It's a vector field, and we can denote that in our index notation as velocity components v sub I in the e hat I coordinate system. Now we're going to take a look at a unit cell through which this fluid will flow. So let me make a little room, and I will draw a cube of material, and we can examine what goes on from one side of the cube to the other and inside of the cube all at the same time. And so these velocity components v1, v2, and v3, we're also going to change the notation up a little bit to be more consistent with fluid mechanics, and we're going to call these velocity components u, v, and w in the x, y, and z directions respectively. So here I have a small unit cube with infinitesimal side lengths dx, dy, and dz. The volume of this cube then is just the multiplication of those three values. So dv is equal to dx, dy, dz. And we have a fluid that has a density and we're going to call that density rho, and that fluid density may change with time. And we're going to put a coordinate system on this. So we have an x, y, and z directions kind of lining up with our cube. And we're going to have fluid that flows through three faces of the cube and flows out of the other three faces of the cube. Now, to keep everything straight, let's identify some points on the cube, A, B, C, and D, and the points on the back face, A star, B star, C star, and D star. And we have a fluid that's flowing. Let's just look at the x direction with the velocity u, velocity component u, that's flowing in that direction. So I'll write a little bit of this down. Fluid flows through the cube in the positive directions of the coordinate system. And so if we look at this face, A, B, A star, B star, the mass into that face is going to be equal to the density times the velocity through that face times the area. Now the dy is the vertical line. The area is dy times dz, and because we're dealing with velocity, we're talking about per time, so we need to multiply that by a small increment of time. Now to check to make sure that we really end up with units of mass, let's take a look at our terms. The density has a mass per volume. The velocity has a length per time. Here we have a length squared and then a time. And so if we look, then we end up with units of mass. Okay, so that is the mass that's flowing into that cube from that direction. Now, again, only looking at what's going on in the x direction, things can happen inside the cube, and we may also have some mass that's flowing out of the opposite side of the cube. So we can look at the mass out of CD, C star, D star, and that will be a similar type of expression. It'll be what's going in the other side plus what happens to it while it's in the cube. So what I mean by that is we have the rate of change of rho u with respect to x. That's the rate of change times what's going on in the x direction, the amount of distance in the x direction, times that area, times that increment of time. Okay, so this is the original plus the rate of change times a small distance. This is a rate of change per distance. And then times the other values as well. So we have things going in, things going out. Things going out may be different than the things going in. But if we consider all the components on all the faces, then we end up with the net mass out will be these rate of change terms. So rho u with respect to x, partial derivative there, partial derivative of rho v, remember that's the y velocity component, with respect to y, and then the partial derivative of rho w with respect to z. Dx, dy, dz is the volume element differential, so dv with time dt. Now if we look at this and write it in our index notation, we can write it this way. If we use our x sub I components, we can say it's the partial derivative of something with respect to x sub I, and this is rho times the vi velocity component. And it's a summation, because we have our implied summation here, and it would expand out to these three terms, and then we have our dv, the volume, in dt. And we've seen this kind of thing before. We have a partial derivative, we have something that is a dot product, and so we can write this as del dot rho v dv dt. And this was what we would call a divergence of rho v. Okay, now we may have some mass in the cell, and we can figure out what that is. We know the density and the volume. So the mass in the cell at a given time is rho times dV. And this itself may change with time. With an amount given by the partial of rho with respect to time, dV dt. So this is the rate of change times time. That gives me the amount of change in that volume. Now, conservation of mass means that the divergence of rho v has to balance against this value. So partial derivative of rho with respect to time for that volume for a small bit of time, plus the divergence of rho times the velocity field, dv dt, has to be equal to 0. So this is like the increase in mass has to balance against the mass flowing out. This is called the Eulerian continuity equation, and we're going to revisit this again after we talk about the Reynolds transport theorem. Okay, so we've talked about the Eulerian description. We have a fixed cell in space, and we watch things that flow past it. So there are a few interesting things that we can do with this. And if you take a class AEM 500, taught by my colleagues, you may get into some of these issues. First thing we can take a look at is an incompressible fluid. Hydraulic fluid, or oftentimes water, is considered to be incompressible in a lot of instances. So if it's an incompressible fluid, then the density is equal to a constant. And I guess we can simplify this down a little bit, since the dV by dt is the same. Probably the way I should have written it at the end was partial derivative of the density with respect to time plus del dot rho v equal to 0. That would be the preferred way to write the continuity equation. So with the incompressible fluid with rho is equal to a constant, then the partial derivative of rho with respect to time is equal to 0. And if that's the case, then we can have the remaining part of this del dot rho v equal to 0. Of course, if the rho is a constant, it can be brought out in front, and we can get rid of that as well, which gives us to del dot v is equal to 0. There's different ways we can express this. We can say the partial derivative of the velocity components with respect to position is equal to 0. Or, if we want to use the u/v/w velocity components, partial of u with respect to x plus the partial of v with respect to y plus the partial of w with respect to z is equal to 0. that's an interesting simplification to this, a consequence of conservation of mass. Second thing we can take a look at is if the velocity field is determined from a potential function. And this is called potential flow. Okay, and in that case, the velocity vector would be determined by taking the gradient of some function phi. And here phi would be a function of x, y, and z, as well as time. In terms of our components, we could say the v sub I are equal to minus the partial derivative of phi with respect to x sub I. And in this case, you can develop what's called irrotational flow. Okay, so some kind of straight line flow. If we use this additionally with an incompressible fluid, so again with an incompressible fluid we have del dot v is equal to 0, and we have v is equal to minus del phi, so we can have del dotted with minus del phi equal to 0. We would end up with del squared phi is equal to 0. We have Laplace's equation. Let's make a little room. We can express that as del squared phi is equal to 0, or we can write it as the partial with respect to x sub I minus partial with respect to x sub I equals 0, or second partial of phi with respect to xi in xi. So now we have a double summation, but it's of those terms on the bottom. We're going to have three terms when we add them together. It's the second partial of phi with respect to x1 twice, plus the second partial of phi with respect to x2 twice, plus the second partial of phi with respect to x3 twice, and then all equal to 0. And when we have this equation and we subject it to the appropriate boundary conditions, then this is the basis for ideal fluid flow. Okay, so those are all kind of interesting things. All right, so next we're going to talk about the divergence theorem. All right, so the previous discussion of the Eulerian continuity equation has given us a physical feel for the divergence of a vector field. We had a very physical application of fluid flowing. But in general, we don't have to be restricted to just fluid flowing. In general, the total spatial change in a vector field in a volume per time is given by, write this down, it's an integral over the volume of the divergence of the vector field A, or we can write this as integral of the volume. The divergence is del dot A integrated over that volume dv, or we can even write it another way, integral over the volume of partial of ai with respect to xi dv. Lastly, we can even expand this out, write it one more time, partial of the component a1 with respect to x1 plus the partial of the component a2 with respect to x2 plus the partial of the component a3 with respect to x3. I've always thought one of the tricky things about the divergence theorem is how often it shows up in completely different looking forms, but it still ends up being all the same thing. So previously, then, we intuitively related this to the amount of mass entering the faces. Or the surface area of our cube. We don't have to be restricted to a cube, though. Notice this volume integral is over some volume, and so more generally, we can express this as, and let me start on a clean page here. This volume integral of del dot A, where A is some vector field, what goes on inside of that volume is balanced by what goes on around the surface. And on that surface is A dot n ds, where n is a unit vector. And so this is usually drawn with this control volume type thing, where this is my region dv. At every point here I have some unit normal perpendicular to the surface. And so what this says is the spatial change of the vector field must balance against the material that passes through the surface. Okay, so on the interior we have del dot A dv, and hopefully that kind of makes sense from our previous discussion. And on the surface we have a surface integral of A dot n ds. So we have this vector field, and we want the projection of that in the direction of the normal. Okay, we add all of that up along the surface boundary, and whatever comes out has to balance against whatever is changing inside that volume. There's all kinds of analogies I guess you could make, but I remember a long time ago, maybe they still have these things, you used to be able to buy rice in a bag that had all these holes in it, and it would fill with water, and you'd pick this bag of rice up after it cooked, and all the water would kind of squirt out. So we're getting the velocity of that through the holes in the bag, but only in the direction that's perpendicular to the normal of that surface. So another way to write this then, sometimes you'll see it this way. A triple integral of the partial of ai with respect to xi dv is equal to a surface integral of ai ni ds using our subscript notation. You may have seen this called Green's theorem, 3 dimensions, Stokes' theorem in 2 dimensions. In general, we can just call it the divergence theorem. And what I'll note here is that we're not going to be able to prove this in this class. It's beyond what we're going to have time for, and beyond what I would be able to explain anyway. So a formal proof is beyond the scope of this class. But we will use it. It's going to be very convenient as a way to relate volume integrals to some sort of equivalent surface integral and vice versa. If you take a class in maybe advanced calculus, that's probably where you would see perhaps a proof of the divergence theorem.